Hi everyone, my name is Neha and this is the fourth lecture on Introduction to Automation. In this lecture we are going to learn about disk direction in incremental optical encoder. So here this picture shows the disk direction in incremental optical encoder. And these are the two waveforms in two different directions. This represents in the counterclockwise direction, and this one is for clockwise direction. So here you see V1 and V2, they represent the photo sensors, and here if you notice that this from the center of these two segments and these two segments is the 360-degree has been taken as a one cycle from slot to slot, and this angle you see here from V1 to here represents the 90-degree. So let's see what will happen in the counterclockwise direction. So if the disk will move in the counterclockwise direction and let's assume one point, then let's assume this point, what will happen? When it will move to the counterclockwise direction, then V1 will be on. I'm assuming from this point this will rotate, so V1 is going to be on for this period of time, whereas V2 this will spend a little bit on time and then it will be off. So that is what is shown over here. So V1 will be on, and you see here V1 will be on during this time, and whereas after this time V2 will be off. So for a small period of the time V2 will be on, and then after that your V2 will be off. So this was the case for the counterclockwise. Now let's see for the clockwise, which means the disk is rotating in this direction. So when the disk is rotating in this direction, so let's assume from this side that this V2 is going to be on for this duration. So when V2 will be on for this duration, then it is represented by this small on, and then it will be off for this whole segment. Whereas if we see V1, then V1 will be off. We are starting V1 from here and V2 from here. So if we see V1, then V1 will be off for this whole segment, and then it will turn on. And that's what we see here. V1 is off for that whole segment, and then it is turned on, and then it will be on for this whole segment, and then so on. So what we observe from this two graph is that in the counterclockwise case, your V2 leads the V1 by 90-degree, and in the clockwise direction V1 leads V2. Now next is decoding the V1 and V2. So in order to decode, we need a decoder circuit. It is used to convert the signal from the photosensors into a binary word. And this circuit has two parts. The first is which extracts the direction information through this reference. And the second part will have down and the up counters, which maintains the slot count. So the up counter, you see here, this up counter signal, it gives one pulse for every slot passed when the disk is going in the clockwise direction. And this countdown signal gives one pulse for every slot passed when the disk is going in counterclockwise direction. Then these signals will be passed to this counter, and from here we obtain the digital position. So the counter, this starts at a 0, which is usually reset by the reference sequence, and then proceed to maintain the position by keeping the track of the counterclockwise and the clockwise direction. Now next we are going to see how to decode the V1 and V2, and to do that we will use D flip-flop along with the two AND gates. Here you see V2, it represents a negative edge triggered clock, and you give the input signal from here, from D, and then you get the two outputs, Q and Q bar. Q usually follows the input. If you, whatever you give over here, it will give the output over here, depending upon the what clock pulse you have applied here. And then Q bar is going to be opposite of what you have obtained here. So here on the right hand side, you see this V2 represents the negative edge triggered clock pulse, and you know that in the negative edge trigger, we trigger it from this side. So this is the negative edge triggering, and this is the input signal, which is shown like this. So what will be the output at this particular case when this is edge triggered, negative edge triggered, and the input is high? Then at here your output is also going to be high. It is going to follow this, and it is going to follow until the next clock pulse arrives. So the output, which is Q here, is going to be high till here, and it will check again and see what the input state is, and here again the input is high. Then it will keep the output state high until the next pulse, and that's how it works. And similarly, in the clockwise direction, this is the input pulse and this is the clock pulse. So here at this, when it is triggered over here, then the input is low, which means the output is going to be low until the next clock pulse arrive. So when the next pulse arrive, it will check the input. It is still low, so your output is still going to be low, and that's how it will work for the clockwise direction. So with the help of this, you can decode the value of V1 and V2 and use it in a counter up and counter down form. Now let's see this problem which says a position sensor system uses a 250 slot disk. The current value of the counter is given, which is this. What is the angle of the shaft being measured? So to measure the angle of the shaft, we need to first calculate each slot. We need to see what each slot angle represents, and that we can calculate by dividing this 250 slot disk, which is already given, by the 360 degree, which is the total slot disk angle. So using this formula, you will get 1.44 degree, and then we need to see what is this value, binary value in the decimal, and this represents 38 decimal. So we know this. Now with the help of this value and this, we can calculate the angle of the shaft by multiplying it with each other. You will get this value, which is 54.72 degree, and this represents the angle of the shaft. Now next is interfacing the computer with the counter and the decoder. So here there is a special problem which comes when passing the data to the computer from a counter. You see this counter, this will receive the real world event from this decoder, and that data is not synchronized with the computer. So for example, if the computer, what I mean is when the computer requests the position data while counter is changing, in that situation computer might get the wrong data. In many applications, this resulting error can be ignored, but in other situations, it is required that data should be accurate. So one solution to this problem is that we can freeze the counter during the time when the computer is receiving the data. However, this is not an effective solution, as when the next clock pulse will arrive, then there would be a possibility that the data will be permanently lost. So the better solution is to have the latch you see here. So with the help of this latch between the counter and the computer, counter is never disabled, and the latch will hold the value of the counter at a particular time, and in this case, with the help of the latch, the data is not lost when the next clock pulse arrives. So this design is better, and with this design you can fetch the information from the counter at a particular time, and that will be the real-time information which you can receive at the computer. So this is the end of the lecture. Thank you so much for watching.